Hi. Today is September 18, and just in 1 minute, CodeTON's round CodeTON will start. We have registered for Division 1 because I am 1900 or greater. These counters are broken, as you see, so it's 52 and it's 52 in a second. Maybe if we restart the page, reload the page, refresh. Okay, they are the same now. Actually, it's the first day that I feel that autumn is coming. It's the first day which is like, I feel cold. Previous days it was more like summer, but today it's not. It's definitely not. It's like freezing temperatures in my room. Let's go. N, K, and X. Find the maximum possible sum of elements in an array consisting of non-negative integers. Ah, it's div1 plus div2, so it's not two separate rounds. Max is K, and elements, all elements do not exceed X. What? So n elements, max equals K equals, and elements do not exceed X. So we really want to make 0, 1, 2, 2, 2, 3, 4, etc. K minus 1, and then a lot of times we do K. Ah, no. A lot of time we do like, we do X. But if X is, let's write this because this is really easy problem. T n kx and cout findance of n kx. And we see that it can be all in int. Okay, so if x is less than k minus 1, then impossible. And because we just cannot make max of k. So if n is less than k, then we also cannot do it. Otherwise, we first of all need all elements from 0 to k minus 1. This is the sum, and after that we need to add, we want to add x actually, but if x equals k minus 1, so if x equals k minus 1, then we have to, are they positive? Yeah, they're positive. So if x is k minus 1, we need to use x minus 1. Otherwise, we need kx. Okay, and then we just say that sum plus equals n minus k times element, and then return sum. Excellent. We will close this. Let's run this. 9? Why 9? 533. It should be 0, 1, 2, 2. So what's wrong? Ah, it should be x minus 1. X equals k, I think. Yeah. Seven minus 1, 57 minus 1, 2007, 39, 800, 1, 2 minus 1. Yes. Great. Problem 2. And we are 600. We're given two arrays. Choose any element B from B. And or everything with B. Is it really an easy problem? So we read end and M. We read A and B. And we print XORs. So here we return PII, where we have const VI A and const VI B. Okay, so what happens here? Actually, where is my... Let's go through the bits. Yeah, so let's consider two cases. First of all, if n is divisible by 2. Yeah, in this case, we just need to do everything that we can to get minimum. We need to do everything that we can to get minimum because we just eliminate all bits which are in one of the b's. And if n is odd, then we need it to do it to maximize it. We just do all the operations. So now we have two questions. What if 2 is not divisible by n and we need to minimize? And what if 2n is divisible by 2 and we need to maximize? Okay, for example, let's solve this problem. We have let's go through all the bits. No, actually, in this case, we do not want to do anything. Yeah, we don't want to do anything in this case because this will only increase and this will only decrease. So, okay. Int n equals a dot size. Okay. Int b equals 0 for int I from b or equals I. Int x equals 0 for int I from a x or equals I, and int y equals 0 for int I from b x or equals I or b y. That's it. We just return minimum of x and y and maximum of x and y. Let's see. 0, 1, 2, 3. No. Why? Yes, now this is fine. You're given two integers n and k. You have an array of size n. And all numbers are from 1 and k. Now we make a two-dimensional array of minimums. For each color, find the smallest rectangle, which contains all the cells of this color. Okay. So if we want to find the numbers of color 3, what we need all columns which are exactly 3 and all rows in which the answer is at least 3 and vice versa. The rows in which it is exactly 3 and the columns in which it is at least 3. Okay, kinda understandable. So this is the problem about 2 pointers. Okay, first we read n and k. Then we read the array A. Actually, it is easier because this array is like square array, so this is nice problem. It is easier because of that, I think. So, if we have at least one number equal to k, then we need a square from the least number, which is at least k, to the most number, which is at least k. And if there is no such number, then nothing. Okay. I think we can make this. Yes, we can. So here we return the I. We take an array. The I-ans of size k, which we need to pass here and here. So first of all, we need to find all the occurrences. So we take PPII sex of size k, and we are saying that they are from n to -1. For int I equals 0, I less than n plus I, if a, no, not if, we say that sex of ai dot x equals minimum of it and I. And y is maximum of this and I. Fine. Okay, now we say we go from 0 to k. And after that we need to advanced sex. So how do we do it? We say that advanced sex.back is just sex.back, and then we go from int I equals k minus 2. We say that advanced sex of I dot x equals minimum of the same, and sex I dot x. And here we need to put I plus 1. And here we say that dot y is maximum of dot y and sex I y. Great. So if sex I dot x is at most sex I dot y, then we say that answer I equals, what is, and actually we need to put, what do we need? We need sum of height and width. So we need to say 2 times this minus this plus 1. Return ans. Finally, we copy this. Four four two 06620 861062. Yes. Problem D. You have an array A of size n with zeros. You have an array of integer C of size n. You have k coins. These days, guys are really fast. Incredible. Incredible, guys. Okay. So, we take. So, what do? We need to find the lexicographically maximum answer. First of all, it's obvious that we need to make the maximum number of any operations because we need to maximize this number. So we need to so we say that we have C equals minimum of all CIs. We say that K over C is the maximum number of operations. And we need to make this number of operations, definitely. Okay, assume that we do it. After that, we need to find the maximum number of operations which we can do with this number. So now we say that C is minimum over Ci, where I is at least 2. Okay, this is kinda a solution. Finally, the number of coins we have. So we find answer of, what is A? We just find answer for C and K. a fine dance of C and K. What do we do here? First of all, we need to find the suffix minima. Suffix minima. I think we can just copy it. Int if I equals n minus 2, I is at least 0 minus I. Ci is minimum of Ci and Ci plus first. So now we have suffix minima. After that, we answer of size n, and we go through 0 to n. So what do we do here? So assume that we already know the answer for 0. We need to make this number of operations. Now we know the minimum on this suffix here. So we need to find so like we have after these operations we have C1, C2, etc. Let's do it from 0. C0, C1, C2, C3, etc. So we know that A0 equals just C0. Oh, it equals K over C0. Now what about A1? So A1 should be... So if we just need to maximize A1, we need to take K over C1. But there's a problem. If this is less than C0, this is incorrect. So, so if C1 is equal to C0, then we just say that A1 equals A0. Now assume that C1 is less than C0. In this case, in this case we can calculate... What do we need to calculate? Let's just do it not for C0 and C1, but for any I. So assume that Ci is greater than Ci minus 1. And we know AI minus 1. So we need to make several operations here so that AI minus 1, like assume that we have K remaining money. We need to do several operations with Ci. So we need Ci minus first times several operations. No, for example, first of all, let's do with Ci several operations x. And also we need to do several operations with AI minus 1 minus x. Okay, and this number should be at most k. So we know that Ci minus 1 times x plus Ci minus 1 AI minus 1 is at most k. So x is at most k minus Ci minus 1 AI minus 1 over Ci minus Ci minus 1. Okay. So we take this x, we immediately spend this money on ci minus 1. Do we? Yeah, we do it. So we have int already like, which is initially 0. Also we say that, no, we do not need already. We need k, which is not int, which should not be int. Also we say that answer 0 equals k over c0. Here we say that if we start from 1, if ci equals ci minus 1, then ans I equals ans I minus 1. Otherwise, we calculate this, which should be at most k, of course. So we say that int x equals, thank you, x equals k minus ci minus 1 times a ans I minus 1 over ci minus ci minus 1. This is x. And we definitely need to spend a I minus 1 minus x money on the previous number. So ci minus 1. And we do it. And after that, we calculate this. Great. Let's see if this was correct. Five zero zero 2 1 2 2 2 2 2 2 2 2 1. Long longs, do we need them? Nah, we do not need them. Long longs are overrated, aren't they? But if I get wrong answer, then I take my words back. Oh. Nice. So this is trash. Maybe our solution is wrong. So what do I say? I say that we need the maximum number such that this is correct. So what is our current state? Our current state is that we have read some prefix I. We have already spent some money on this. And we know that everything will be fine if we spend at least AI operations with I. And we need to do it. Okay, this is our current state. So what is the next state? So if ci plus first, okay, let it be I minus 1. If ci equals ci minus 1, then we just are in the same position. Yeah, we have enough money to cover this. And we can do it. And if we do it, then everything will be satisfied. So assume that ci is less than ci minus 1. We want to maximize ci. We want the maximum x here. So we say that ci times x and all the remaining money should go to the previous stage. So ci minus 1 times ai minus 1 minus x. Is it most k? So we have this formula, of course. Maybe we cannot. Maybe x sometimes is greater than a minus 1 here. And it shouldn't. Yes, sometimes I think sometimes it is just greater than a minus 1. Yeah, I think it is greater than a minus 1. So we need to take minimum of ai minus 1 and this number. So can it be negative? No, it cannot be negative because if I take x equals 0, then this is fine. What's wrong with you, ants? Can we find some control test, or I should just submit this? I think it should be easy to do. Like, for example, we have 1,000. No, like, we have 49 money, and this costs 10, and this costs 11. Then I have the following inequality. 11x plus 10 4 minus x, at most k, at most 49. And I say that x is at most 9, but actually x is at most 4. Yes, let's check it. So now my solution is this one. And if I put 2, 10, 11, I will get something crazy, won't I? What's wrong with you? Ah, I need the amount of money, which is 49. So it says 49, which is really crazy. Yeah, it definitely is. So what if I replace this with this? Now it says 4, 4. Which is fine. Okay. Okay, this happens, so we are not upset. We go to problem E. $309. Oh man. You're given an array of size n of integers a. You can choose a set of non-overlapping subarrays. Calculate max of the elements. calculate max of the elements and calculate bitwise XOR of this element. What is the maximum bitwise XOR that can be obtained? Okay, the obvious thing to do is just to include all elements, and in this case we just get the max of all numbers. And this is the minimum that we can do at it's something that we can definitely do. Okay, now assume that we have this is the biggest one here. So what we need to do is to fill this with ones, if possible. Yeah, so we need at least one segment source of the obtained max values. This is not a nice operation. We definitely need to have this one. Let's go from the left to the right. So first of all, we need this one, and this means that we have some segment in which we have, for example, this is kth 0. So we need all numbers 0, 1, etc. 2 to k minus 1 here. And actually we can find all such segments because there is at most this number of segments at all. Okay. We have this. What next? Okay, we need to have this k minus 1, for example. How can we do it? There are two ways. First way is to extend this segment so that it contains k minus 1 as well. And the second way is to find some other segment which contains 0, etc. k to k minus second, but does not contains at least one of the numbers this. Actually, all the numbers are at most n. Because there is no need to make them very big. Yeah, I got it. I got it. There is no need to make them bigger than n. Because max is impossible to be greater than n. Actually, this is kind of Bitset's problem, isn't it? It's a ruffle from something new. And because let's just iterate over all subsegments, and for each of them, we store the set of all possible subsets. The set of all possible XORs, which is from 0 to 2 to 30 minus 1. Okay, so we store it. And how do we recalculate it? How do we recalculate it? Actually, do we need some sort of XOR convolution? So we have some element, we iterate over all segments. Each of them gives some number n. Yes, so we have some sort of n squared operations of sorts like, take a bit set of size. Isn't it huge? Like 500 squared, 5,000 squared half, so like 12 million. Then also we have some sort of bit sets, which are this number. It's like 100. Yeah, it's like 100. So okay. It's kind of huge. So what do we do then? What do we do then? After that, so we have some bit set of what we can achieve. So we need to make a XOR convolution with a number very fast. How can it be done? How can we make a XOR convolution really fast? Yeah, we can do it in like. So if we want to XOR with a number, we need to iterate over its bits. No, this is way too slow. This is way too slow. To XOR with A, we need to iterate over all its bits, and if it has like 2 to the k, then we need to take this number end with it and move it right, and end with it and move it left, and OR them or XOR them. I don't know. But we can OR only one. No. So we need, what do we need? We need some. So okay, what is like answer for I? This is, first of all, we just can ignore the ith element. First of all, this is bi minus first. Or what we can do otherwise. Otherwise, we need to take some segment. So we take sum over all j which are at most I. We take max of segment from j to I. Then we need to XOR convolve it with the answer for j minus 1, like. We can say that bi is the sum for elements which are less than bi. Okay, then bi is either bi minus 1 or sum for j which are strictly less than I, max of from j to I exclusive, XOR convolve with b j minus 1. Okay, we need to make this XOR. So if we do it naively, the asymptotics is sum for all I, then sum for all j which are less than I, and after that we need to make XOR convolution which can be done in. So this is n squared half. And what is the asymptotic for XOR convolution? We iterate over all 13 bits, and if it is true, we need to like make five bitwise operations. So like 5 times n over 64. So this is 65 and this is 64. So this is n cube halved, which is like 62.5 billion, which is really too much. But I think we do not do this XOR convolution really many times. For example, assume that we have considered this segment. When do we need to consider this segment. So we only need to consider this segment if this segment didn't do everything that we can, and this segment also didn't. So if XOR of this segment is different from these two, this only can be if these two numbers are equal. And since they are equal, and also if they are equal, then after we have taken this, again, I don't understand. So we have some segment, we have some element. Which segments we are interested in? Are we interested in this segment? We are interested in this segment only if this segment has different max. So this number, for example, let this segment be S, then this is max of S. Okay, but isn't this segment really good? This segment. So if this segment is T, then this element is max of T. So we only need to do it if max of this element is different from two other maxes. We can just write it, I think. Because why do I spend so much time on this? So do I have bit sets? Yes, I do. So we read N, we read A. It's so funny that this guy say that bitset should not be in author's solution, then he prepared this contest. We just return I and we count I. So here we say int answer, which has the I of A. Okay, let's write a solution. So we want vector bitset of size 8192. We make bitset of n for each prefix, so like n+1. We say that b0, the only possible XOR of it is just 0. Then we need to do something for every prefix. we do something here. And finally, we need to find the maximum number in the final bit set. So if b and I, then return I. Otherwise, just return 0. So what do we do here? We say that first of all, bi is just bi minus first. Yes. Secondly, we need to iterate over all j minus less than I and take max XOR convolved with this number. Fine. First of all, we need to find all maxes. So this is vector, vector, int maxes. Now let's calculate them. So we go through 0 to n. This should be of size n and again of size n. No, we need to start from each element and end with I think n plus 1. Okay. Yes. We go through, we say that we have set of int s. We fill it with all numbers from 0 to, okay, at most n, let it be s insert I. After that, we go from g equals I, j, I plus 1, j is at most n, and we say that mx I, j first of all, we need to remove number a j minus 1 from this set. Okay, and now we say that mx of this is just the first element. Great, now we know all the maxes. So I have actually two different optimizations. The first optimization says that I do not need to make these XOR convolutions all the time. I only need to do them once when the max changes. And the next is that I only need to do them if so I have ith element. So assume that I have already considered all these segments. I have already considered all these segments. What do I do then? I then need to consider one more segment. How do I do it? So if this max is the same, then I only need to add this answer. Actually, I don't need. See? I don't need to do it. So assume that this max is the same as this max. In this case, it allows me to add this to the answer, but I do not need this because this is submask of this one, of this segment. So I don't need to do it. So I just ignore such places. I only need such segments where this is different from this. So assume they are different. Do I now need to consider them? Answer is not always yes, because I have already considered this MEX in this answer. So if I want to consider this segment, then let it be, let this MEX be K, and let this MEX be M. Okay, so they should be different. If they are not different, I do not consider this segment at all. This means that I is greater than K. And MEX of this whole array is something. Okay, if this changes, actually this MEX is just I. Okay, this MEX is I, and then I add number I. So if this changes, then if this is number J, then this MEX is J. So I have some middle, and middle plus I, MEX of middle plus I is just J, and MEX of middle plus J is I. Is this possible? Yes, it's actually possible. It's possible because I can have like a hole here and a hole here. And this is M. Then MEX of M plus I is J, and f of x MEX of M plus J is I. But in this case, and there is only also something there. Fine, fine, let's do it. Maybe this will be fast. I hope so. Okay, let's go. I go through all segments in J equals... What is this? I start with 1, I think. Okay, so what do I do here? I say, let's try Bj plus segment from J to I. So let's say we have current MEX, which is equal to 0. So if MEX of J I equals... Okay, I do not need current MEX. MEX of J plus 1 I. If this is true, then I do not need it. Continue. Okay, this optimization is applied. Also, if this segment has same MEX, then I also don't need it. So if MEX of J I minus 1 equals MEX J plus 1 I, then also continue. Okay, otherwise I need it. Otherwise I need it, and I say that bi or equals XOR convolve of bj with number MEXji. Let's find the XOR convolution. Okay, I don't need it. I can just... Or do I? No, I need it. Let's move it here. Let's say that we have using bit equals bitset n, and we return bit here. Const bit. I can just copy it. Bit b and constant k. And we return b. I spent a lot of time, guys. We iterate over all numbers. So if k and 1 over I, we need to XOR shift b and I. Okay, now we have to do void XOR shift of const of bitset b and const int index. Yes, we need a static array of bitsets. Shifters. And if shifters is empty, we need to fill it. After that, what do? We say that return. First of all, we need to apply b and shifters I dot first. Then we need to move it to the left. I can just say that b equals this. So first of all, I need to move it to the left, or I need to move it to the right. So I need to take b and shifters I dot y, and this. Okay. What are the shifters? We say that shifters dot resize b, then we go for int I equals for b less than b. We say that we iterate over all numbers, and if if I and G, then the first should be true. Otherwise, the second one. Okay, I have written this ugly solution 2670. S is empty, but why? Because this. Two two five zero. This is quite not true. Why is it 2? We need to look at these bit sets at every moment. Okay, let's look at them at every moment. What is the answer, by the way? We can XOR this and... Actually, this is easy to make 3. Why didn't I notice that? Maybe because my XORs, mexes are incorrect. Let's look. So I need mex from 0 to 3. This is 3. So why? Okay, assume that I have I equals 3. So first of all, I have bi equals... Why so ugly? Okay. So j, I need j equals 0. So yes, correct, and I do XOR convolve. So this b is this, k is 3, and I need to make a XOR convolve with it. How do I do XOR shift? So let's look at the shifters. I need ith shifter. What is the ith shifter? I is 0, so I need the 0th shifter. No, this is empty. This is because I needed to do this and this. Now it is 0. No, this is really not nice. Now we jump here, we have j equals 0, and we make XOR convolution. So how do we do it? So here we have shifters. Shifter 0 is... No, it is not correct. Ah, this is because I needed to do second, I believe, and otherwise first. Okay, now I jump here, and what do we see? We see that this shifter is correct, and this shifter is also correct. And for example, this should be 8 ones and 8 zeros. Yes, this is totally correct. And now B should become... Yes, this one. Okay, so now it should be with the third one. Yes. Is it true now? Again, now it's 6. And 6 is the right answer. Okay, let's again run everything. 2670. Okay, I think we just believe that it is fine. I think we just believe it is fine. Wrong answer process 2. Let's make some tests, I believe. So like 5 numbers. We do 0, 1, 2, 3. And then 0. What is the answer here? 4. No, the answer should not be 4. Yes, the answer should not be 4 because I can make 5. Okay, let's do it easier. Let's make an easier test. I have 1, I have 3, and 0, 1, 0. So the answer is 3. It says 2. Okay, but why? It says 2. So first of all, it says that I can make, what is BI? B3. It says that I can make 0 and 2. Can I make 0 and 2? Here. I can make 0. I can make 1. I can make 1. Why isn't it included? I can make 1. Are you retarded? I believe actually we can have j is less than I minus 1. And in this case, no, why is it? Why did it skip? So what is mx ji? It is 1. Why did it say... should have done this. Yeah. Okay, so now it says 3. Yes, and this says 5. Okay, let's try again. Sometimes errors happen. Time limit exceeded on test 7. It is not fine. It's not fine. But I don't think we can speed up it a lot. Because XOR convolution is not a really fast operation. Let's try some random test. So we take vi a of size n, and we fill it with, for example, let's take numbers less than 2000. We say that if numbers at most 2000, say that ai equals let's stop at example this number, put seg here, no, put rng here, and we need to print find ans of a. Okay, in debug it is slow, but it is fast in release. No, it is not. What is slowing it down? This operation is slow? This operation is slow. I didn't know that. Okay, let's do it the fast way. So the fast way is we take a vector of int of size n plus 1, or even bool. We have like int current mex equals 0. Okay, now we go through these numbers and we say that v of this number is false, is true. Now, while we put this, and while this we increment MEXij. Okay, it should be much faster. It is much faster. I didn't know that sets are so slow. Why is it 25? What? Two six seven zero 5 3. Let's try again. So now we have no slow sets. I didn't know that this would be a bottleneck. This was a bottleneck. Okay, I messed up. Now I'm 300 something. So you say that 255 people have written this so fast? Nah. Nah, you're kidding me. 45 minutes on a problem. Oh no. Hmm. Why? Why is it so fast? Huh. Okay, we have numbers from 1 to n. We sort them, we write them in base k. Now we need to find the number of numbers such that their position is same in lexicographical order as in normal order. There shouldn't be many of them. Shouldn't be many of them. Okay, so if k is at least 10, then of course answer is just n. But if not, then I don't think the answer is big. Always 1 is the first one, so this is fine. Are there some other numbers starting with 1? I don't think so. I don't think so, because like if the number starts with 1, yes, if it starts with 1, dude, this is awful. And also I think that some of my problems can fail on system tests. Okay. Okay. So we have a number. In normal life, it is greater than anything before it. Yes? So which is shorter or less. So we need number of numbers such that number of k which are less than n but lexicographically bigger is the same as the number of numbers which are greater than n, but they are lexicographically smaller than n. So these numbers should be equal. And what I think is that usually these numbers are way too different. One of them is way bigger than the other one. For example, let's assume that n starts with 2, or at least 2. Yeah, then it is greater than all numbers think we can already write it, can't we? No, maybe not. So, for example, 2. What is the number of numbers which are less than 2, but lexicographically bigger? In the worst case scenario, when it is just 2 and a lot of zeros, still the number of such numbers is huge. Is it worth solving some other problem? I don't believe so. Rainbow actually solved this problem in 1.5 hours. No, we don't want it. So again, number of k which are less than n, then less than x, for example, but k is greater than lexicographically than x, is equal to number of k which are greater than x, but they are lexicographically smaller than x. Okay, this is easily calculated. Yeah, we just iterate over the length of this number. So first of all, we need to find the numbers which are the same length than x. The same length as x. And the number of such numbers is okay, let the length be n or k, no, l. Okay, so it is x minus, no, I cannot use k because I have already used, okay, m. So x minus k to the power l minus 1. This is number of numbers the same length as x, but smaller. And they are all lexicographically also smaller than x, so I'm not interested in them. Okay, I'm interested in numbers which are strictly less by length. So sum for L equals 1 to length of x minus 1. So let's take all numbers of this length. Number of at most this length. Number of such numbers is k to the power of L. Yes. Now I need to subtract numbers which are at most x lexicographically. This is kinda x over k to power x minus L and also minus 1. Okay, this is the answer. Okay, let's check it. For example, I have number 20. So I will get this minus this. No, first one. And 10 minus 1, which is 8. And actually I have numbers 3, 4, 5, 6, 7, 8, 9. There are only 7 of them. So I messed up. I messed up. No, this is 7. Yeah, I didn't mess up. For example, if I have 21, then it's the same. Okay, this is the formula. And I need to sum it over all numbers. Okay, what about bigger numbers? Again, if we have the numbers of same length, we are not interested. We only need the numbers of bigger length. So let's take a number of bigger length. Actually, this means that I only need numbers. Okay, which numbers x I'm interested in? I am definitely interested in numbers which are at least 2 digits and which are less than n digits. Why? Because if not, then there are just no numbers which are, for example, greater than x but less lexicographically, or vice versa. So we only have 2 different lengths. Length between 2 and size of n. Fine. Fine. Now what do? We calculate it. So we have sum from L equals 1. No, not to 1. X plus 1 to, for example, modulo n minus 1. So how many numbers which are bigger than n but smaller lexicographically? For example, 20. If I want a number to be bigger but less lexicographically, I need at most 199. So the minimum number which is not good, is just k to L minus x times x minus 1. Oh, plus 1. This number is no good. And what is the minimum number which is good? It is just k to the power L minus x. Oh, yeah, this one. No, no, to the power. So L is length, isn't it? L is length. Yes, L is length. So x is of length L. So, no, L, x is of length modulo x. So I need to multiply it by, yes, by this. And now I need number with L digits, which is k to the power L minus 1. Okay. Okay, so what? So now I have this, and also for the final size there is something else. Let's rewrite. Pause. Okay, let's continue. So okay, and in the end there is something else. Because in the end I need minimum of this number. So here I need k. So here I need maximum of 0, and I can take here no, I can take minimum of n plus 1 and this minus k to l minus 1. Oh my. Ah, here I need n minus 1. Yes. So I want to say that actually the right size, the right part is usually bigger than the left part. Yeah, the right part is definitely at least. So this is at least the maximum number here. Which is the maximum number here? So it is k to l minus, what is l? N minus 1 minus x times x minus k to l minus 1. I wrote it 2 times. So the maximum number on the left is like k to the l, k to x minus 1 minus x over this minus 1. And also there are some other numbers, so this is the sum of these numbers. And I want to say that right part is bigger, so here I also need n minus 2. Usually this is bigger. Okay, for example, let's take it twice. This is totally enough. Okay, let's take this. n minus 1 minus x. What do we have here? X minus this minus this. Okay. This is a number. This is definitely a number. I can't solve it. It's a huge mess. I need like several hours to solve this problem. What's happening here? What the hell is going on? So this is something like just simply x to k to x minus 1, I think. Something like this. This is the upper bound, minus 1. And here we have this number. And they kinda can be of the same scale, because x can start with something like this. And also there is this number, which is also kind of big. So we have n plus 1 minus. So we can actually add 1 here, something like this. How do they solve this problem? This is painful. Guys, are you crazy? How do they solve this problem? So if this is at least this, then we are fine. So we can iterate over all x's and consider the number of zeros in the beginning of this number. Okay, we can do it. What after that? So if this is at least this, then simply no. Then simply no. So let's assume that x minus k to x minus 1 is less than k to 2x minus n. In this case, we have so k starts with so x minus 1, then a lot of zeros, and maybe at position 2x minus n minus 1, it can have something. Here we have 1, then a lot of zeros, and here we can have something. So what's the answer for such number? What is the answer for such number? Again, let's iterate over numbers to the left. So sum of L equals 1 to x minus 1. Okay, so I can say that x equals k to x minus 1 plus y, where y is less than this. And I need to find the number of such y's. So k to the L actually y is less than k to the z, where z is at most 2x minus n minus n. Minus 1. Okay, let's rewrite it. Yeah, because this is just sum of k to the L minus, and this is k to x minus 1 plus y. No, plus minus 1. Let's rewrite it again. So here we can divide. We see that it is k to the L minus k to L minus 1. Then plus y over k to this minus 1. Sum of such numbers. Okay, let's sum this up. So this is a telescopic sum which converts him into k to x minus 1 minus 1, then minus 1 times this number, so minus x actually, and minus sum of all these numbers. Okay, so this is the left part. 13 minutes to solve this problem. Great. A lot of time. On the right side, we have k to L minus x times x minus k to L minus first. Let's rewrite it again. So we have here that this is k to L minus x times. Okay, this is just upsolving. Actually, I have lost my international Grandmaster, and now we have a bit of upsolving. Maybe I can hack somebody. Can I hack somebody? Are there hacks possible? I don't think so, but maybe. My room. I don't think hacks are possible here. Oh, people don't hack anybody. Okay, well deserved, I guess. Why is all these people solve problem F? What's wrong with you? So x is k to x minus first plus y. Okay, and we see here that these and these destroy each other. So we just have the following number. K to L minus x times y. Okay. Which is, by the way, y times this sum. This sum is k to n minus x minus k over k minus 1. Okay, this is this great sum. I see the people solved the problem with bitsets very fast, and I didn't. People really solved it fast. Okay, so these three bad attempts were actually not good. Let's look. Let's look. Unsuccessful submission is -50. So let's assume that I add 150 to me. Now it is 500. It's still very bad if I add 150. Let's look at my submissions. 1, 2, 3. So 150. No, this is not enough. I should have just solved this faster. For example, see, this person solved all 5 problems in 30 damn minutes, and he will get +1 for this achievement. Piotr seems to not like the problem E. Why Codeforce's predictor does not predict Umnix rating? I already remember that last time I saw, it didn't predict it. Pathetic. Let's continue maybe. Okay, so we have this number. And we are interested if this is equal to what number? To this number. So k to x minus 1 minus x minus this sum. So we have a fixed n, a fixed x, a fixed size of y. Assume that we add 1 to y. So y increases by 1. Okay? What happens to this number? No. In the end, I also need to add this minimum. I need to add it here. Okay, so assume that we add 1 to y. Then actually this number increases and this number decreases. So there is at most 1 y with such equality. Okay, if so, why is it so big here? Where is it? Daisy numbers. Why is it so big here? So it will be like it shouldn't be so big. Yes, I think that with every length there should be at most one number. So why is it 3789? Maybe I don't understand something. Let's try and solve this problem. I don't know. Let's look at at some sample. For example, 33 and 2. So we have numbers like 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. No, I'm too lazy. This is a way too big list. Okay, this is our numbers. Now let's rewrite them in lexicographical order. So we start with numbers length 1, and this is 1. Now we need to write 1, 0, of course. Understandable. Now we will write more zeros. These are in pair. Okay. So now we have 1, 0, 0, 0, 1. 1, 0, 0, 0, 1. 0 is not there, so I can reduce it by 1. Ah, and they are in pair. Okay. Okay, this is the same number. No. Something is strange because I don't have all the numbers. I don't have all the numbers here. Okay, I see here. Here I should have had also this number. Hmm. Okay. What now? 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So what are the pairs which we needed? Okay. I see this pair. I see this pair and I see this pair actually. So why is it so big here? It shouldn't be so big. Maybe it is not monotonic actually. No, this increases exactly by 1 each time, and this does not do it each time. I don't get it. Again, let's fix our length of our number. Assume that it is okay. Then if we increase it by 1, the number of numbers so if x is exactly n minus 1, then this formula is not correct. No, it is correct. It is always correct. Okay, maybe. Okay. The only issue is that these numbers are equal. So n minus x is. But how? Okay. It should be. No, shouldn't be. Yes. If n is x plus 1, then actually this numerator is 0. So x equals n minus 1 is an extra case. And here shouldn't be L. What is L? For God's sake. It is n. N. Okay. So in this case, here we have minimum of n plus 1 and k to the power and kx just. I believe so. So actually this is possible. It is possible for this number to be equal on a segment. And in this case, these numbers are equal. Okay, I believe. Let's try the solution. It begins to be adequate. But actually, I will not be able to submit it because system testing is still pending. Minus 53. Why minus 53? You know, if it is exactly minus 53, I will lose my international Grandmaster title. For the first time for more than a year. And for what? CodeTON contest. What is my place actually? 286? So I will get $8. You understand? I'm rich. Yes, this is a pity. Let's upsolve this anyway. I think at least we can like stress with some other solution. Okay, so we have several cases. First of all, if k is greater than n, then all numbers are 1 digits. And in this case, no, greater than n. We return n. Okay. Second thing, 1 is always the first one. So we calculate answer is 1. Now, let's look back here. Actually, let's assume that I'm already talking, saying editorial to you. So in this problem, we need to calculate a number of numbers n and k such that if you write all these numbers in lexicographical order based on their base k representation, then how many such numbers that on the ith position there is the representation of number I. What I did in the whole contest is I calculated the formulae for this. So, the first observation that I will say to you is the number of the position. So I need number I to be equal to its position. So what is the number I? This is the number of j such that j is at most I. This is the number of such numbers. What is this number? It is the number of such j that j is lexicographically at most I. And here should be I. So what we need for these two numbers is to be equal. So first of all, in both of these parts, there is I, because I is at most I, and I is lexicographically at most I. So let's get rid of it. So now we calculate the number of j such that j is less than I, and it should be equal to the number of j such that j, let me write it like this, precedes. Precedes means lexicographically less. Fine. Now there are like Euler's circles, or in English literature, some other circles, I don't remember. So these are the numbers where j is less than I. And here are the numbers where j is less than I. And there is somewhere a number I. Okay? So we need for these two sets to be equal. And this means that we need these two sets to be equal. Okay. So now I need the following. I need the number of j's such that j is less than I, but j is also lexicographically bigger than I. And it should be the same as the number of j such that j is bigger than I, but j is lexicographically smaller than I. So these two numbers should be equal. Let's note the following fact, actually. Let's notice the following fact. Assume that j is a good number. Or j is just some number with some left part and some right part. Let's look what happens when we add 1. Let's look what happens when we add 1. So here we have numbers. No, I. Sorry, I. We increment it by 1. So this is I and this is I. So here we have numbers which are greater than I, but lexicographically smaller than I. And actually, so this set, the numbers which are greater than I, is decreased by 1 number. I plus 1 was greater than I, but now it isn't. And usually it is not included in the other set. Usually I plus 1 is lexicographically bigger than I. The only case is when you have like 999, you added 1 and you get 1000. Or something like this, where you have a lot of 9s. Only 9s in your number. In this case, the number was greater than I, but lexicographically smaller than I. This is the only way that I plus 1 is in this set for I. But you definitely get numbers like, so at most -1. At most. But you get always numbers like 10i, which is, no, like 10i plus 10, for example. No, like 10i, for example. 10i, or for base k, you get ki. It is greater than both these numbers, but it is lexicographically smaller than I plus 1. And also, all numbers till ki plus k minus 1. All these numbers are lexicographically smaller than this number. And this, we can also look at this part. And here, actually, the following happens. So, if we increase I by 1, again, let's assume that the number of digits is the same in numbers I and I plus 1. In this case, also both this is true and this is true. So it's not interesting in both of these sets. I plus 1 won't be there, and okay. So we're interested in a number of numbers which are less than I, but lexicographically bigger than I. Notice that if two numbers are of the same length, then actually it is equivalent to be less than number and be lexicographically less than number. So we are not interested in numbers of the same length than I, as I. So since j should be less than I, we are interested in numbers which are shorter than I. So length of j should be less than length of I. So I will look here. System testing. So for these numbers, this is also always true. And this can only become false. Yeah, so if j, it maybe was greater than I, but now it is not greater than I lexicographically because I increased. Maybe the left part didn't change, but sometimes it changes. And the right part, so if we have I and I plus 1 of the same length, then this minus 1 is not possible. So we can only increase or stay the same the right part and decrease or stay same the left part. So we have two functions. The left part is decreasing one, and the right part is increasing one. So the place where they are equal is just some segment. It may be empty. It may consist of 1 point, or it may consist of several points. But this is just a segment. So actually, if we just can calculate these functions fast, it is easy to solve this problem. So let's assume that we have the function f, this is f, this is g, and we have f minus g. We get some increasing function, non-strictly increasing function, which has some zeros. And we want to find the set of all zeros. This is easy. You can just write a binary search. So in terms of C++, if it was a container, we could write like, if this is V, we could write upper bound of v.begin, v.end, and 0. And this will be the first positive number. After that, let's write lower bound of the same things and 0. And this will take us to the first number, which is at least 0. So after we subtract them, we will get the number of zeros. And this can be done for every length. Actually, for just every length. So now we need to calculate these functions. Yeah, so we actually just need to calculate these functions. We can now go to the beginning. We just need to subtract the right number from the left number. Yeah, and this is our function. And we need to calculate it fast. So we need actually to calculate number of j's which are lexicographically smaller than I. This is the only thing that we need to calculate it fast for each I we want. How can we do it? So assume that we have some number. What is the number of numbers which are lexicographically smaller than I? Let's iterate over their length. So let's iterate sum of all size of j equals 1 to size of j equals n. Let's iterate over the length of the number j. In this case, we want j to be... Let's do it like this. It will be easier, I think. Okay, we want j to be at most... No, it won't be easier. J should be less than I. Okay? Actually, I think we will consider two cases. Let's write it like this. Number of j which are less than I. Let's rewrite it as this sum. Sum of j's till the length of I minus 1, number of j's which are less than I, and plus sum of length of j is I till n, number of j's less than I. Let's consider these two things. So here, need numbers of j's which are less than I. They should be just shorter than, since they are shorter than I, they just need to be at most number of j's which are at most I over k to the power of length I minus length j. So why is that? For example, let's assume that you have some number I, and you want to compare it with some number j which is shorter. You need to do the two things. First of all, you need to remove these 3 digits. Why is 3? Because 3 is the difference between I and j. So I remove them as follows. I just divide by the base of our number system to the power the difference of these two numbers. After that, I just need to compare these two numbers, and j should be at most I. So this is the inequality. How can I calculate this number? Sorry, I will rewrite it one more time. I need it till n minus 1 because it will be easier. And finally, we have only one thing, number of j's, which is less than I, such that the length of j is n. So I will have 3 addends. So here I need the number of j's which are at most I over this. And this is easier to calculate because I just need I over this. This is the number of numbers. This is just the number of positive integers which are at most j, which are at most this number. Now we need to subtract the number of numbers which are too short. And to find them, we need to subtract the number of short numbers. Yeah, for example, if j length of j equals 3, for example, let's k equal 10. Yeah, so j is like 1 to 4, maybe. In this case, we need to subtract all numbers which are 2 digits or less. How many numbers which are 2 digits or less? There are 99 of them. In general, the number of short numbers is this. Number of short numbers is this one. So we can just subtract them. No, plus 1. Plus 1. This is 99, we need to add 1 back. So this is the first addend, where we have here I minus 1. Let's calculate the second addend. So sum for j from I plus 1 to n minus 1, I over, not I over, number of j's which are at most I. No, not I, which are lexicographically less than I. Okay. This time we have j which is longer than I. How many numbers then? For example, let it be 1, 2, 3, 2. We cannot have 1, 2, 3, 2 because whatever we put here, it won't be less than I. So we need actually this part to be strongly less than I. So what I want to say is that this number should be strictly less than I. Let's rewrite it. It just means that j should be less than I times k to j minus I. Yes. J just should be less than I times k to the length j minus j length I. So, what is the number of such numbers? Number of such numbers is I times k to j minus I minus 1 and minus the number of shorter numbers, which is again k to j minus 1 plus 1. So we get the formula I times, like, okay, let's write it like this. K to j minus 1 times I times k to j minus, to I minus 1. No. Sorry, just a second. I think I plus 1. No, because it's incorrect. I should have written I here. Hey, I don't want it. Let's just write it as it is. Let's save it like this, okay? I times k to j minus I minus k to j minus 1. So this is the formula. Finally, the case when length of j equals n. It's kind of the same, but instead of j being less than I times k to n minus I, there is the second thing that we need to satisfy. It also should be less than n plus 1. So it should be less than minimum of n plus 1 and this number. And as always, this means that we need I times we need minimum of n plus 1 and I times k to n minus I minus k to j to n minus 1. If this is the answer for n. Now we need to write it. And actually this is not really hard. Actually people fail on system tests on problem C, don't they? But only gray people. MEXanization. Okay, whatever. I can just don't do it. I can just answer it quite fairly. So, first of all, we need to find the length of number n. How do we do it? It is easy to do. So we say that length is 0, and while n, we need to plus l, and n is divided by k. So first of all, we find the length of n. Now we iterate over it. Ups I equals 1. Ups I is at most ups n plus ups I. So we need to make a binary search. Let me think. Let's write a function which finds the lower bound and upper bound. So like int long lower bound of long start, long finish, and some function, which we will write as bool function of bool of long does not know what is function. Takes a function predicate. So it returns minimum number. Okay, let's just let it return long. Minimum x with positive value. Or finish. And UB will be minimum x with non-negative value. Okay, let's go. We need to ask ourselves. So while finish let me think. So the answer is actually between start and finish So MEXanized is finish +1. So while y is greater than x +1, we need to do something. After that, we just return x. So we say ll m equals x plus y half, and we want to check whether it is the answer or not. So is it true that it is the minimum x with positive value? So we need to check m-1. So we calculate predicate of m-1. So if predicate m-1 is positive, then m cannot be the minimum x with positive value because m-1 is also such. So we say that y equals m. Otherwise, x equals m. Okay, and here is the same thing, but non-negative value. So here we say that now we need the function. So after f which is from which checks long x and it checks the answer. So first of all, it needs to subtract x minus this. So we have 3 addends. And we need to subtract them all. How do we do it? And I will actually now write the answer. So little ans equals 0. We say that ans plus equals ub of something minus lb of something, and we return answer. What is something and something? The minimum number of length ups I is some power of k. So what is the maximum number which is allowed? What is the minimum number which is not allowed? Minimum, let's call it finish. In the end, we actually need to multiply by k. So if ups I equals ups n, then the minimum number is n plus 1. And otherwise, it is pk times k. So now let's calculate these 3 addends. Let's start with zeros. Let's start with zeros. So first of all, we need this one. So we sum ups j equals 1, ups j is less than ups I. What do we do here? Let me just increase this for your comfort. So I divided by I actually need all these numbers pre-computed. Let me pre-compute these numbers. So I have VL powers of k of size ups n plus 1 and filled with ones. And I say that pk of I plus 1 equals k times pki. And here I have pk ups I minus 1 and here I also have pk minus 1, and here I have pk ups I. And here I do not do anything. Okay. So here when I iterate over these j's, I divide I by k to the power I minus j, which is this, and I subtract k to the power j minus 1 here I can write I, use I here, pk power j minus 1 plus 1. Now addend 2 is iterated from I plus 1 to n minus 1. So from ups I plus 1, y plus 1. No, I think just from I, not from plus 1. Ups j is less than ups n plus ups j. And I add something to addend 2. What? I add this difference. So I times power of k j minus I minus k to the power j minus 1. And finally, addend 3 is addend 3 is the same thing, but with minimums. So here we have minimum of n plus 1 and this number. And here we have ups n, and here we also have ups n. What is this? This is I. Okay, I think we have written this. Now we need to debug this. But I am afraid it is still system testing, so we will not be able to do it. All zeros, of course. Actually, for length 1, it shouldn't be zeros. For length 1, it shouldn't be zeros. It's just not here. What's happening? 1 n is 2, and ups n is also 2. Great. Ah, okay. So we have some sort of predicate in which we iterate from start to finish, and we need to find minimum x with positive value. It should be 2. I think it should be 2. No, it became 1. Why? Why is it 1? So it tried 2 and it decided to go down. So we have predicate for 1. Ah, because it shouldn't be I, it should be I minus 1, I guess. The number of numbers which are less than I. Okay. Still, I don't believe this answer. So is now, okay, first is now 2. What about this one? Yeah. Now the answer is definitely not just 1. It's minus 2. What? Ah. It's still some mess. For example, what is wrong with 6-4? Let's look at 6-4. Okay. The lower bound should be just 2. No, it's 4. It's definitely not correct. Yeah, it's definitely not fine. Let's look again. So m, for example, 3. I think. So for number 3, the number of numbers which are less than 3 is 2. But the number which are lexicographically less, there are a lot of them. There are 1, 2, 4, 5, and 6. They're all less than 3. 3 is actually the maximum number in base 4. And definitely it's fine. No, what? So if predicate is at least 0? I think I messed up with this one. Again, so if predicate is greater than 0. Ah, no. What? Predicate is greater than 0, I should look in the left half, don't I? So if m minus 1 is greater than 0, this means that m cannot be minimum x with positive value, because m minus 1 is already with positive value. if the answer is negative, just a moment. I believe I need to subtract the other way. So this minus I minus 1. I believe this is correct way. And now we have 1, which is correct answer. And maybe here is also the correct answer. 2, 2, 1, 3, 1. But then there is 0 here. And the answer should not be 0. What is this answer? Also didn't find 1 here for some reason. I think not finding 1 is easier to solve. Let's look here. Okay. So we have some predicate. It found some great number which has non-negative predicate for some reason. Let's look at this. So we have number 235101. Let's come again. No, I want a non-negative predicate. I want a non-negative predicate. So 352524. Okay. What? So now it will be non-negative for some reason. Let's go. So we want to find a number of numbers which are lexicographically smaller than our number. So non-negative. It will be non-negative. It definitely will be non-negative. What? Ah, of course. What I don't understand is why. Okay, it is non-negative. Okay, maybe I don't understand why the first one is negative. Yeah, because this is negative, of course. Why is that? So we have number, this big number. And this one is negative. Ah, this one is negative for some reason. And this is because this number is huge. Yeah, I shouldn't have done this. So this is just an overflow issue. To fix this, we need to find the minimum properly. One way is to use int 128, but I will not do it. Instead, if you have cool trick from me, if you have numbers A, B, and C, what is the minimum of A and B times C? Assume that C is greater than 0. In this case, let's calculate A over C. So if it is at least B, then this means that A is at least BC, and we need to choose BC. But if A over C is less than B, then we need to choose A. Okay, do we have some number among these two which is totally positive? And yes, there is. Actually, both these numbers are positive. So LL minimum equals n plus 1. But if minimum divided by this number is at least I, then we need to say that minimum is this product. And in the end, we put this product here. Let's recalculate again. And there it is. 1. Now the answer is kinda fine. Are we able to submit now? We are able to submit and we get accepted almost instantly. So this is not really the hardest problem in the universe, but still it's not like my type of problems. Maybe. A lot of people get system tests failure. Maybe this means that I will stay international Grandmaster. But no, minus 53. Still minus 53. Okay. Okay, understandable. Totally understandable. Should have been faster and shouldn't have been sent this and this in the system. Let's go with problems A from A to E, and I will explain them. Problem A. We have numbers n, x, n, k, and x. Find the maximum possible sum of elements in an array consisting of non-negative integers which has n elements, its max is equal to k, and all its elements do not exceed k. Let me explain this beautiful problem. Sorry, it's a bit laggy because I have deleted too much. Okay. Problem A. N, K, and X. X? Yeah. So we need AI is at most X. Length of A equals N, and we need max of A equals N. Oh, no, K. So to get max a equals k, this means that 0, 1, etc. k minus 1 are in the array, but k is not in the array. So this means that actually length of a is at least k. And as we see, length of a should be n. So the first case, if k is greater than n, then impossible. Let's continue now. Assuming that n is at most k, then this means that we just can take these numbers. Or can we? Actually, it's still not always possible, because sometimes x is really small and it's less than k. If x is less than k, or less than k minus 1, so if x less than k minus 1, this means that we just can't take k minus 1. And this means that we cannot get the max of k. So, continue our solution. If k is less than... No. What is k less than k minus 1? Did I write like this? Or didn't I? Yes. So if k is greater than x plus 1, also impossible. Okay, now assume that these both do not hold and we do not break from our function. This means that actually we can take all these numbers. And actually, in this case, the answer is possible, because it's easy to just add a lot of zeros, for example. And the max is still k. Now the question is, what is the maximum sum? We cannot change these elements, because they are already fixed. They are from 0 to k minus 1. But we can change these elements. The only thing that we shouldn't break is this one. K should not be in the array. So let's see. Can we just, if we want to maximize the sum, we just want to take the maximum possible numbers. In this case, the maximum possible numbers are x's. Can we just take a lot of x's? Yes, we can, unless x is k. So if x is not equal to k, then we can just take all the remaining numbers as x's. And this will be fine, because max is still k. And the sum is maximized. What will be the sum then? The sum will be the sum from 0 to k minus 1 and plus several times x. How many times? N minus k times, because we have in total n numbers, and we have already spent k numbers here. There is a short formula for that, but you can just not use it, because the problem allowed it. Yeah, you can just solve it in O of n easily. If you want, you can just sum this in cycle. But if you do not want, there is a short version, which is k times k minus 1 half plus n minus k times x. Okay, this is if x is not equal to k. Otherwise, the best we can hope for is x minus 1. And actually, the same is true. We take k numbers here. Here we take x minus 1, n minus k times. And the answer is k times k minus 1 half plus n minus k times x minus 1. Or shortly, I think you can write like this. Half plus n minus k times No, forget it. Just do it with an if, and this will be fine. You don't need to do it more shortly. Problem B, friendly arrays. We have two arrays, A of length n and B of length m. We can take some element of array B and OR it with all elements in A. We want to maximize or minimize the answer. How to solve this problem? So assume that we have an array A. Yeah. What if we apply all operations? So we take all B first, B second, etc., Bm, and apply it to this now array A. So if the OR of this array is B, then actually you have ORed all the elements of A with this number B. So actually each element is as big as possible. You added some, you didn't change bits which are outside of B, and all bits which are inside B, they are set to 1. So what now is the XOR? Actually, let's do it this way. So there are two types of bits in our numbers. So the first type of bit is the bit which is present in B, and the number, and the bit which is not in B. So for these bits, you just cannot affect them in any way. Since these bits are not in any of the BIs, you just cannot change them. So on these positions, the answer is already fixed. You cannot do it. You cannot do anything. So let's just look at the other positions, which are B in B. Yeah, these positions are simply ignored. Let's just remove all these positions from all the numbers because they do not do anything. So let's assume now that all our bits are from B, which I'm looking at. So in this case, each of these numbers is just became B. Again, this is B because although it can have some other bits other than B, we ignore them because they already should be in the answer. We cannot change them. So we pretend that they do not exist. So all these numbers just became B. What is the XOR of a lot of B's? This is just n times XOR B, nth multiple of B in XOR group, which is 0 if n is divisible by 2, and B if 0 is not divisible by 2. And notice that actually you cannot get the number less than 0. So if you have several bits, you cannot make them less than just all zeros. And you cannot get them more than all ones. And B is just all ones on the important positions. Let's call these positions important. So on non-important positions, you cannot change them at all. So we pretend they do not exist. And all important positions can be either zeros or B's. So as you see here, it is important to know the parity of n. So let's consider two cases. 2 divides n and 2 does not divide n. And also we have two types of operations, minimization and maximization. We have already actually solved two of these problems. So if n is even, then it is easy to minimize our number. We just need to or every number with B. Yeah, because in the end, all important positions will be nullified. And this is what we want. Also, we solved this problem. if we want to maximize the odd array, we also need to make all the important bits 1. But now, because now the OR of these bits becomes 1. Because each of these bits will be 1, and after the odd XOR, it will still be 1. Now we have the only 2 problems left, which is maximization under the condition that 2 divides n, and minimization under the condition that 2 does not divide n. And this is where my brain stopped working during the contest, because I thought, well, now we need to iterate which A's should get which B's, and this is total nonsense, because in the statement it is said that each BI, if we choose it, it is applied to all A's, not just one of them. It is applied to all A's. So in these kind of problems, the answer is same even if we can apply BI not to all numbers, but just to some of them. It's still the same. But in case of these 2 problems, it is important how to explain. Let me think. For example, let's assume that you have 2 zeros and you have B first equals 4. What you would like to do is to apply 4 to only one of these numbers. So now they are 4 and 0, and their XOR is 4. This will be a maximization of this array. But you cannot. According to the statement, you need to apply them to both numbers. So you will get 4 plus 4 equals 0. So if you look at this in this perspective, you will see that actually, if you have an even n, and you want to maximize the answer, you are not interested in doing any operations at all. If you do any operation and b has some bit b, this bit will be 1 in every number. But since the n is even, after the XOR it will be nullified. So you just do not need to do it. You just stay. You just put the numbers, leave them the same as they were. The same goes in this case. Assume that we have the odd array and we want to minimize it. If we apply any operation and bi contains some important bit b, now in all of these numbers, the bit b will be set to 1. So in the XOR, this bit will be present. And so, therefore, you increase the answer. Or in the best case scenario, you leave it the same. And we do not want it to be increased. We want it to be the same at most. Or even be lower, but we cannot make it lower. So in this case, actually AI is the best we can hope for. So how do we calculate the answer? Actually, very easily. First of all, we just find the XOR of all numbers. After that, we calculate the XOR of all b's. After that, we calculate the c, which is XOR of... No, sorry. Not XOR of all numbers, but bitwise OR of all numbers. And then we calculate the XOR of all numbers plus of all a's or b's. Like this. And then the minimum of a and c is actually the answer for the minimization problem, and maximum of AC is the answer for the maximization problem. You can see it here. You just do not need to know which either n is even or odd. You just need to take the minimum of these 2 numbers, and it is the answer for the minimization problem, and take the greater answer among these 2 for the maximization problem. Or you can look at the parity, and if n is even, for example, then here it is division sign. Okay, let me write in C++. If n is even, then we firstly print C, then A. Otherwise, firstly we print A and then C. Okay, this is the answer. This is the solution for problem B. Now let's look at the problem C. I'm still international Grandmaster, guys. This is the best day of my life. Minus 50. We are still international Grandmasters. So today is the great day. Colorful table. We are given two numbers n and k. Array of integers of size n. And each number is from 1 to k. Then we take the two-dimensional array, which is minimums of column number and row number. And we want to find the minimum rectangle, which contains all numbers equal to I. The idea is called bounding box. Assume that you have several objects on the plane, and you want to find the minimum rectangle. Let me just draw some rectangle, whose axes are parallel to the coordinate axis, and which contains all these objects. How can you just set the rectangle? So how can you express the rectangle as several numbers? You actually need the coordinates of the leftmost and bottom angle. Bottom left, I think. It's called bottom left and upper right angles. You need these four numbers, the coordinates of this angle and coordinates of this angle. And what do you know? For example, u, which is the y coordinate of this side. It should be at least each of these numbers. So you can just say that u should be maximum of all yi, where these numbers are xi and yi. Similarly, r should be maximum. Sorry, let me just write like this. It should be at least maximum, because it should contain all these numbers. Similarly, r is at least maximum of xi. L should be at most minimum of xi. And d should be at most minimum of yi. So this is the set of inequalities that guarantee that your rectangle contains all the points. Actually, this is an equivalent criterion. So if you have these inequalities, you get all the points. And if you have all the points, you have to follow these four criteria. So now we need to find the bounding box, which is the minimum possible box, which contains all these numbers. And to get the bounding box, you need to just take equalities here. So all these four inequalities should be just equal signs. If you have them, then your solution works. But this only works if there is at least one point in the set, of course, because if there are no set points in the set, then there is no bounding box. Okay, so let's see at our problem. We have a square, and we have the array written here and the same array written here. And in each point, you write the minimum of these two numbers. So here we'll have minimum of AI and AJ. And the problem asks you to find the bounding box of all numbers equal to I, where I is from 1 to k. And write something like the sum of height and width of this rectangle, but we will just find the all rectangles. If we find all the rectangles, we can find the sum of their coordinates as well. So how do you approach this problem? First of all, you need to ask yourself, is there just at least one number equal to I? The answer is interesting. Actually, it is equivalent. So Bij contains contains some number x. Let me write it as x. Equivalent to AI. Let me write it as set. So this is a sequence, not a single number AI. So these two things are equivalent. Why is that? So if you have some x in array AI, then actually you can find this number on the diagonal. So assume that this is number x and this is also number x, because these arrays are same. Then here we will have x. So x will be in this array. And the vice versa, actually. If you have some number x here, this means that at least one of these two numbers is x. But this means that x lies in this array. How do you fastly understand if x is in the array? What you can do is to make a counting exercise. You just take the array like CNT of size k, which is initially zeros. And you iterate over. I wrote k here because in the beginning we can assume that I decremented all the numbers, so they are now from 0 to k minus 1. The solution will be the same, but it will be more convenient for me to use indices starting with 0. So for int I from array A, we make plus plus CNT of I. After this procedure, you will get for each I the number of i's in the array A. So if let's go from 0 to k. So if CNT I equals 0, then just return 0. I mean, because the bounding box is empty. Otherwise, it is not empty. Yeah, it is not empty because actually it should contain at least one element, II. So, for example, let's look at this number x, which we are looking for. Still, let me write x here. Okay, so we have number x. So in these columns, there can be some x's, but on which positions? Actually, on each position where there is at least one. So it should be at least x here in order to here be an x. And if the number is less than x, then it wouldn't be x here because it will be less than x. So the bounding box actually bounds out the numbers which are at least x. So the bounding box should contain all indices which are at least x. The same goes for columns. So the bounding box for x should contain all numbers which are at least x. And this is the criterion again. If you have all numbers which are at least x, then you contain all the x's, because outside this box, if we have some x, then either this or this lies outside the box. But all these numbers are at least x in order for the minimum to be x. So bounding box is bounding box for all x's in the B array is the Cartesian product of two bounding boxes of numbers which are at least x. So now you have the following problem. Given the array A, calculate fast bounding. Since this is 1D problem and not 2D problem, let's call it bounding segment. LX RX for all x in from 1 to till x of numbers which are at least x. Let me call these two numbers, these two letters, capital ones. It will be useful later. So, to do it, let's firstly find all bounding segments LX, RX, which are small letters. Again, for all x from 1 to k of numbers which are equal to x. So first of all, we need to find the segments for numbers which are equal to x. And this is done in the same fashion as counting. So let's reminisce the cycle about counting. So it said that for int I from 0 to n, we said that plus plus cnt of ai. And actually, in this cycle, we can also maintain these segments. So in the beginning, let's make two vectors, L and R, and L will be plus infinity, and R will be minus infinity. Then we can say here that LAI is minimum of LAI and I. Okay, because the leftmost position of the number I is no righter than I itself. And in the same fashion, this should be maximum of RAI and I. So doing this, you can find these lowercase bounding segments. So how you now calculate the capital letter segments, which are for numbers which are at least x. And let me know that if there is no number I in the array, so if cnt I equals 0, then in the end li is a plus infinity still, and ri is minus infinity, because we just didn't change them. And in the beginning they were plus infinity and minus infinity. Okay, so if there is no such number in the array, then this holds. What if cnt I is greater than 0? We have some segment. Now let's calculate r, I, and li. The easier thing is actually k minus first, so the biggest L and R. Why is it the easiest one? Because this is, let me remind you, the set of positions such that AI is at least k minus 1. But all numbers are from 0 to k minus 1. So this is equivalent to the number being equal to k minus 1. So actually this segment is just k, it is lowercase k minus 1 segment. So this segment is easy to find. What about this one? To answer this question, let's think, what is the difference between this segment and this segment? Actually, this segment contains already all numbers which are k minus 1s. And in order to get to this one, we only need to add numbers which are k minus 2s. but all such numbers are already in LK-2, RK-2. What we would like to do is just take the union of them. So we would like to take LK-1, RK-1, cup LK-2, RK-2. But this is not always possible because the union of two segments is not always a segment. For example, in this case, if we have such segment and such segment, their union is two segments and not one. If they were overlapping, for example, like this, then their union would be a segment, but not in this case. So instead of that, since we need a bounding segment, we just need to make it convex. And to make it convex, we just need to take minimum of LK-1, LK-2, and maximum of LK-1 and RK-2. So this is our segment LR. And this pattern continues till the end. So to calculate these bigger segments, you can do the following. So for int I equals, so you say in the beginning that LK-1 is LK-1, RK-1 is RK-1, and you go from the beginning to the ending. And also, let's already calculate the answer. Oh, no, let's do it in the end. So, starting with k-2, what is Li? It is minimum of Li plus 1 and Li. Notice that if Li is plus infinity, it doesn't break anything because minimum with plus infinity is just the same number. In the same fashion, Ri is maximum of Ri plus first and Ri. Okay, that's it. And in the end, you can just print the answers because answer ith is 0 if Li is greater than Ri, or equivalently Li is plus infinity and Ri is minus infinity. And Ri minus Li plus 1, this is the side of this rectangle. And if you need the both sides, you need to double it up if Li is less than Ri or equal to Ri. This is the solution to the problem C. Let's go to the problem D. We have n zeros. We can pay Ci coins and add 1 to all elements from the array A on the prefix, I mean. So for each prefix, we know the cost of adding 1 to this prefix. And we need to find the lexicographically largest array A that can be obtained. Let's find it. So we have the array A. Let's array C. Let's write it as this. First of all, let me explain you the motivation. So we know that A0 should be biggest possible. And notice that A0 is incremented during each operation. So each operation increases A0 by 1. So if we want to find the lexicographically biggest array, then we in particular want to maximize this number A0. And this means that we want to maximize the number of operations. So let's write it. We want to say that K is like Ci first plus Ci second plus etc. plus Ci t. And we want to maximize t. what is interesting here is that let C0 be the minimum of the array Ci. Then you can write that this number is at least C0, and this number is also at least C0, and etc. This number is also at least C0. So in total, this is at least T C0. Then you can divide and find out that actually T is at most K over C0. Okay? Great. But actually, this number T is achievable. So actually, let me write it like this. A0 is this because, as I said, the 0th element increments during each operation. So the number of operation is the number A0 in the end. Since we want to maximize the lexicographical array, we want to maximize A0. So we want to maximize this number. We want to maximize this number, and this is at most K over C0. Actually, it can be equal to K over C0 if we just take all operations with C0. So we know A0. We know it. Let's go on. What about A1? So I think most frequently C1 will be same as C0, because the only way C1 is greater than C0 is C0 being the minimum, the only minimum actually. Most frequently C1 will be equal to C0. And in this case, actually you can assume that this C0 has index Ci where I is greater than 0. And in this case, actually A0 will be equal to A1. And since you cannot hope for the better, you cannot hope for A1 being greater than A0, because each operation increases 0, but not every operation necessarily increases A1 by 1. So actually, it is easy to see that A0 will be at least A1, and A1 will be at least A2 in the end, and etc. The array will be non-increasing. So as I said, if C1 is equal to C0, you can assume that they are equal and go on. But if C1 is less than C0, then something incredible happens. So assume that you make exactly... this means actually that you need to make some x operations with C0, with 0th element, and pay x C0. Plus, you need to perform A0 minus x operations with A1, or with something greater than A1. Sorry, I messed up. Oh, no, I didn't mess up. Actually, what I wanted to say is this one. Let C1 be the minimum among C1, C2, etc., C and minus 1. So let C1 be the minimum operation which increases the first element. And the only way that C0 is greater than C1 is that C0 is actually the only minimum. So C1 was greater. Sorry, it should be other way. In this case, as I said, let's assume that we spent x operations on C0 and the other operations on C1. the only thing that we know is that this should be at most x. This should be at most x. This means that x times, and also of course x is between 0 and a0. This is what we also know. We can rewrite it as this, such that c1 minus c0 with minus plus a0 c1 is at most k. This means that x is at least a0 c1 minus x over c1 minus c0. Actually, this is not the luckiest representation because this can overflow. Yeah, because c1 is just a number no more than 10 to the 9th, and this is also a number which is at most 10 to the 9th. This is not the best way to represent it, so let me rewrite it the other way. Let me say that y is the number of these operations, and x is the number of, and x, which is a0 minus y, is the number of these operations. So let y equal a0 minus x. So we can say that a0 minus x minus y c0 plus a0 minus y, which is, sorry, minus x, which is just y. Is at most k. You can say that now y is at most 1 times c1 minus c0 is at most k minus a0 c0. And this time this cannot overflow because actually this is money that you have already spent. So you have already spent this money on the 0th element. This cannot overflow. So y is at most k minus a0 c0 over c1 minus c0. But you want y to be the biggest possible. Actually, what I want to say here is that these x operations are fixed in stone. You cannot do anything but apply them to the 0th element. And these y operations are not fixed in stone. And we want to preserve the maximum liberty for us. So what we want to do is to maximize our freedom, we need to maximize this number y, which is at most, which should be taken in this case minimum of a0 and this fraction. Let me write it as floor division. So this is our y. We want to take it equal to this number. Also, we can say that actually k now is decreased by a0 minus y times c0. Why is that? Because, as I said, these x operations are already set in stone. We need to spend them on the 0th element. If we spend at least one more on the bigger elements, then there will be not enough money to make a0 equal to a0. So now we have the following position. We have now k, which is less than k initial. We already know a1. Or do we? Do we know a1? Yes, we know a1, which is actually just y. Yes, we know that it is y. Why is that? Because we can just spend x operations on the 0th element and C0 and y operations on the minimum elements on the element C1, this one, which increases the first element and has the minimum cost. We can then continue the same process. So let me now explain what is the temporary position. So temporary position is the following. After we have processed the first I indices, we want the following. First of all, we know. Let me write what we know. First of all, we know A0, etc. AI. Secondly, we know remaining K, which can be spent on elements greater than I. So everything which is not in this K from the initial K, I is already spent here and there is no way to do it otherwise. Okay, and also, okay, and that's it. We know all these numbers and we know the remaining K which can be spent on the right side. And let's add that everything in left part except the AI operations applied to ith element are set in stone. You cannot change them. They are already spent. They are outside K already. So this is our state. We already know the answer for the prefix. We know how much money we have already spent on these numbers. But we still haven't provided the answer AI to this number. Because we still don't know which operations will do it. So maybe we will just use CI all the times. Or maybe we will, for example, 2 times use CI and 7 times use C I plus 100, for example. We still don't know it. The only thing that we know is that we need to somehow distribute AI operations in this segment. This is what we know. We want to somehow distribute AI operations in this segment. Okay. Assume that we have this situation. Let's calculate AI plus first. Again, let's assume that we know CI plus first, and this happened to be equal to CI. This guarantees actually that if we spend all our elements on CI, all our money on CI, then these operations will provide AI once into this element. Since we know that CI equals to CI plus first, we can actually spend all this money, the same amount of money, actually, on the I plus first optimum on this element. But this time, this element will not only nourish this element, it will also nourish this element as well. AI plus first. And so AI plus first will be equal to AI. And this is fine. We will get the same position. We know the all elements from A0 to AI plus first. we didn't spend any more keys. Everything in the left side except nourishing this element is already set in stone. And we need to distribute this number of operations now. Okay, let's continue. Assume that ci plus first is greater than ci. This means that possibly, maybe we cannot spend all our money on this thing, because in this case, the number of operations will be less than AI. Why is that? This can be if k over ci plus first is less than k over ci, which is actually equal to AI. This is possible because ci plus first is greater than ci, as I said, and since we have the greater denominator, we get the lesser fraction. Maybe they are still equal if the floor sign removes the difference, but sometimes it doesn't remove the difference, and in this case, we cannot spend all our operations on this element. We need to think. How do we think? We say, okay, we have to spend at most y operations on I plus first elements or greater. Okay, so let's assume that we spend some I operations. Some y operations on elements which are greater than I. And the rest of the operations we just spent on this element, which happens to be just ci. AI minus y times. So this should be no more than k. And as you can see, according to the definition, all these numbers are at most ci plus first. This is because ci plus first is the minimum of all costs which are greater than I. So these numbers are all at least ci plus first. So k is at least this thing, which is ai minus y times ci, or ci like this. And these elements, but we changed the elements to their estimates. And the estimate is y times ci plus first. This should be at most k still. And then we rewrote it as y is at most, y is at most ci times a, it is at most k minus k minus ai times ci divided by ci plus first minus ci. And also y should be at most ai, of course, because we cannot distribute more operations that we have at all. And actually ai plus first is at most y. We cannot, or even equal to y. So y is just the number of operations which cover a plus first element. And ai minus y is the number of operations which do not cover them. So we have the following estimate, that ai plus first is at most minimum of ai and this fraction. This estimate is actually exact because you can really take this number and take ci plus first this number of times, and take ci the other number of times, and you will see that both these numbers are at least, are at least 0. And the money spent is at most k because of this fraction. This fraction is written in the manner that you get it at most k. So this is possible to get this number equal to this minimum. So we just say that ai plus first equals this minimum. Let me rewrite it accurately so you can write in your solution if you want. So it is minimum fi and k minus ai times ci divided by ci plus first minus ci. And this can be taken arithmetic division, not the float point division. What I want to say is that we actually did everything that we wanted except this part. Everything in the left part except the AIs is set in stone. We still didn't set in stone the operations applied to AI. They are still lying in K. And this will lead to incorrect answer because the solution, if we just continue it, it will assume that we have this number of operations and we can distribute K money on these operations. This is not true because some of this money, namely AI plus first minus AI minus AI plus first times CI. This money should be spent on this element, on the ith element. You cannot spend it on anything else, or else you will not get the optimal answer. Therefore, we need to subtract it. And after you do it, you're all right. It is interesting to notice that you cannot get overflow here because still this number is just at most k. You cannot overflow here. So you can just write the whole solution in ints if you desire to do so. The last thing that I wanted to say is that these CIs. So as I said, actually CI in parentheses is minimum of CI, CI plus first, etc., Cn minus first. How to calculate them? Actually, you can just go from the end to the beginning. So you say that Ci minus n minus first. Let's again use capital letter and small letter. So Cn minus first is Cn minus first. And we go from n minus 2 to at least 0. And we say that Ci is minimum of Ci plus first and Ci. And if you perform this, you get capital C, which is Ci with parentheses, and you can calculate everything that I said earlier. And finally, problem E. And this is a awful problem because it is Bitset problem as spoiled by... Actually, I think we can find the humorous comments already about this. Let me ruffle about it. No jokes about E. I guess maybe E is not. It is not mandatory to use bit sets in E. Is it? Okay. It is not. Mandatory to use bit sets there, I guess. Let's actually try. Let me try the solution without bit sets. Okay. And here I will not use bit sets. Okay, the only thing where I use bit sets is XOR convolve and here and here, I guess. Okay, so let's not do it. I think let's slow it down a bit. So here we say, for example, bit answer answer I equals b I XOR k and return answer. Okay, I think it shouldn't be fast. Let's try. Okay, and here I say make OR of bi XOR convolve. And make OR will also make the OR step very slow. Void make OR of bit B and bit C. Const bit C. We can go from bit 0 to n, and we say that bi or equals ci. Okay, bi or ci. Will it now work fast? Will it now work correct? No, it won't. What? Ah, the input is incorrect. Let's try to submit it. Also accepted? No way. Okay, let me... Fine. Okay, let me explain the solution for problem E. So, you're given array A of size n, and you want to find non-overlapping arrays of this array. With maximum XOR of mexes. How to solve this problem? Okay, let's wait until this thing unstucks itself, unfreezes. So first thing that we'll need to have is the array of all mexes of all subarrays of the array. This is what we'll do. Come on. Okay, assume that you have an array. Okay, this thing died. What is that? Okay. Whatever. So, first thing that I want you to understand is for all ij, to calculate this array, ij equals max of ai, etc., aj minus first. To calculate this 2D array. How to do it? Let's, for the beginning, do the following. We have some array. Calculate the maxes of all prefixes of this array. For example, let me make an example. So this should be 0th should be 0, 0, 0, 3, 4, 5, 5, 5, 5. So each element represents this subarray. This element, for example, represents this subarray, and so on. How to calculate such maxes? So all maxes on the prefixes of the array. Actually, we also need this one, which represents the whole array. In order to do it, first of all, my slow approach. If you have an array of size n, then max is no more than n. You can just take the set of ints. So then you put there all numbers from 0 to n. And after that, what is the max? Max is the minimum number which is not in the array. Let S be the set of elements which are not in the array. Then you can do the following. So for I, first of all, we say that M0 is 0. And then we say that for I equals 1, I is at most n plus plus I. So let's think, what is the difference between 0 I minus 1 and 0 I? This is the I minus first element. We added it into our segment. So since we added them, we should remove it from S, because S is the set of elements which are not in the array. So we say S.erase of I. And now, since we have erased it, we can say that mi is the minimum element that is still not in the array. This is s.begin and star. Okay, this was actually very slow because you do not need to use sets here. I was really surprised, but you cannot make like 5,000 squared operations with set. It is not. It's not feasible. So the other way is to do the following. You store the CNT array of size n plus 1 again. So with indices from 0 to n. And it says how many elements are there which are equal to I. So again, we say that m0 equals 0. And we say the following. For int I equals 0, from 1 to at most n, we do the following. First of all, let's try that mi is just mi minus first. What is the only way that it can be not it? It can be larger if mi minus first is actually the element that was added right now. So as I said, 0i and 0i minus first are different in this element. So let's add it. We say plus plus cnt of I minus first. If, no, not I minus first, sorry. Actually, I messed up 2 times. Here it should be AI. And here it should be, here it is okay. So we plus plus cnt of AI. And if after that this element is same as mi, then actually mi is not mex, because mex is the element which is excluded from the array, but we have it here. So we need to do the following. While mi is at least, no, while cnt mi is at least 1, we need to plus plus mi. Okay, what is the complexity? At first glance, this cycle can make n operations. And it can. Yeah, for example, if we have this array, in the end it will make n operations. So since you have n here and n here, you may think that it is n squared. But this is false. Actually, the complexity is O of n. It is so-called amortized complexity. So the real complexity of this cycle is O of n, but amortized complexity is O of 1. Because each time that you run this line, mi is increased by 1, and mi cannot be greater than n. So actually the maximum number of times that you do this line is n. So maximum number of times that you make this line is 2n. Yeah, because each time you check this condition, and each time not counting the last one, mi is increased by 1. So actually, if you apply amortized analysis here, you get that this whole cycle is O of n, and no O of n squared. And this is O of n log n times big constant, which comes from the set. So you do not do it actually here. So this is how to find all mexes on all prefixes, but how to find all mexes on all subsegments? Actually, to do it, you just iterate over all suffixes of the array, and for each suffix, all subsegments starting here are just prefixes of this suffix. So you run the subroutine which I already explained to you earlier for each suffix. So you get the array mij, which is equal to mex of ai, ai plus first, etc., aj minus first. Great. Let's continue. Assume that you have calculated this array. Then how to calculate the thing that is asked in the statement? Actually, let's say, so we have array a0, etc., a minus 1, a n minus 1. So there are n prefixes of this array. Prefix 0th, prefix first, etc., prefix nth. The ith prefix contains I element from the beginning of this array. What I want to do is I want for each prefix calculate this set of all possible answers in ith prefix. What is the set of all possible answers? So I want to consider all possible sets of non-overlapping subsegments here, non-intersecting subsegments, counting mexes in these subsegments, counting XOR of these mexes, and if this is the possible answer j, then I want bij to be equal to true. So it is true if and only if j is achievable XOR in ith prefix. And ith prefix is just a0, etc., ai minus 1. So let's begin with the beginning condition and ending condition. So what is a0? A0 is simply the array consisting of 1 and a lot of zeros. Yeah, since in the 0th prefix you do not have elements, so the only possible XOR is just 1. So you'd need this XOR. What is actually what is actually an what should be the size of this bit set? I mean, it is easy to see that all mexes are at most n. So all XORs actually are less than power of 2, which is greater than n. In our case, it's 2 to the 13, which is 8192. So you need these arrays bi to be of size 8132. So b is just vector bool. Okay, if you have it, what is the answer? Answer is actually maximum I such that a n I is true. And this can be found using a cycle. So the only thing that is left is knowing a0, etc., ai minus first, count ai. If we do it, then actually everything is fine. Okay. Let's assume that we have first I element. What can we do? First of all, we can just ignore this element and find the answer for the previous subsegment, and this is just bi minus first. Otherwise, you need to take some segment which ends here and add all possible answers to this answer. So the naive thing to do is the following. Bi minus first is or over all j from 0 to I minus 1 of the following thing. First of all, we need to take mex from j to I. Then we need to make XOR convolution of this number with bj. That's it. What is XOR convolution? Actually, it's rather simple. So assume that in bj, the indices of ones are like, let's somehow write them, I first, I second, etc., I kth. Then in some number t XOR bj, these indices are t XOR A1, I1, t XOR A2, etc. t XOR IK. Sorry, it should be I here. So the operation of XOR convolution with a number just shifts each index of 1 to some other position, and this position is the XOR of the initial position with some fixed number. This is what I called XOR convolution. You can do XOR convolution in O of n time easily. You just construct a new array, iterate over the old array, and if you have some 1 there on the ith position, you put it here on the ith XOR something position in the other array. So the XOR convolution operation is very easy. You do it, and that's it. So if it were fast enough, you would get OK. The problem is it is not very fast. So you have the outer cycle of length n, which is because we iterate over I. Also, there is a cycle of j, which is like n half because we do not go to the n, we go to n half. And here, the next problem is this thing of XOR convolution requires n time. And also, actually, we also need I time here to like add all these vectors together. But okay, something like this. And this is kind of huge number because this is sort of 5,000 cubed half, which is 62 billion or 63 billion. This is too big. This is unacceptable. And there is some optimization. And if you implement this optimization, it gets awk, actually. We will, I think, look into the tutorial and understand why it works. And now I will just explain this optimization. So assume that you have some MEX of some segment. And it really is useful. What do I mean by that? I mean that it is not in bi minus first. Yes, I think it's just, it is not in bi minus first. So why is it useful? It's useful because you can, I think, okay, let me rephrase it like this. Since let's consider segments from the ending to the beginning, so in this direction. So I call a value f1 gained, let me write it like this, a 1 in mji, this is I minus first actually, XOR convolved with bj is useful if we still didn't get it neither in b I minus first nor in j prime greater than j. So if we didn't see this one before, then it is useful. So if we do not have any useful ones, then there is no need to consider this segment because it will not change the answer. The answer is only changed when we see some useful ones which weren't seen before, and they are added to the answer. Okay. Actually, there is no really many ways to increase the answer. For example, assume that you have this segment. Why isn't this segment good? Why isn't this segment good? Actually, many times it will be also good. So what I want to say is that many times mj minus 1 I XOR convolved with b, sorry, no, not j minus 1, but I minus 1. Many times this will happen, that this contains mji XOR b. So in other words, everything which is achieved with this segment is also achieved with segment which is one less. This is true if these two XORs, if these two maxes are equal. So if these two maxes are equal, then you can just remove the last element and get the same answer. But actually, this same answer is already counted in bi minus first. So bi minus first is the answer for the I minus first elements without this one. So if this is not needed, then actually the answer is already calculated here. And we do not need this segment. So we only need this segment if, so let me rephrase, if mji equals mji minus 1, then continue. We do not need it. Also, the other thing to know is that actually, redraw it again. So let it be our big segment. Here we have I minus 1. Here we have j. Here we have the segment. Actually, I want to say that sometimes this segment is already okay. So I want also to say that if mji equals mj plus 1I, then also continue. Because assume that it is there. This means, sorry, assume that they are equal. In this case, mj I XOR b j, this is what we are counting in our place. But actually, this is contained in mj plus 1 I XOR b j plus 1. Why is that? Because these two numbers are equal, and this number, or this set of indices, contains this one. So let me draw like this. So this one is contained in this one. And since this is true, actually this set is greater or equal than this set. But this set is already considered when we consider this segment. So there is no need to consider this segment, because we have already considered this segment, and it had already all such ones that we could get from this place. So this means that actually this is useless. We can also continue in this case. And otherwise, let's do it naively. So if these both this is false and this is false, then actually let's do the XOR convolution in O of n. And what I want to say is that actually on average there will be not n operations here. There will be like much less, maybe logarithm of n or just one operation, but it will be much faster than n cubed. It will be like n squared. So I hope that we will find the explanation in the editorial. So let me open it and let's see it. Yes, blah blah blah, iterating n cube. Yes. Yes. Okay, and he says that there are no more than n times 2 irreplaceable segments. Irreplaceable segment is the segment for which these two things didn't continue. So this is not equal to this one and this one. For each irreplaceable segment, let's look at the larger element of the pair AL, AR. Let's assume AL is larger. And let's prove that there is at most one segment where AL is the left element and it is larger. Suppose there are at least two such segments. Okay. So let's prove that there are no more than 2n such segments. Let's consider this segment, AJ, AL. Let me do it as in the editorial, so AL and AR. AL and AR. So I want to say that, let me write mx of L R equals what I used to name L R parse first. So this is the max of all numbers from Lth to Rth inclusive. So the max of these numbers. So we spent O of n time there when max LR is not equal to either neither this one and nor this one. So we want to prove that there are at most 2n such segments. Actually, we will prove that there are at most n such segments where AL is at least AR, and at most n such segments where AR is at least AL. So in total, at most 2n segments. Let's prove it. So assume that in total there are 2n segments. Assume, for example, let's look at these 6 segments. So to prove that there are at most n such segments, I want to say that there are no more than one segment with this L. So assume the contrary and assume that there is AL, AR, 1, and also there is a segment AL and AR2. And they both are irreplaceable. So these two inequalities hold. What they want to say is actually that MEX, let the MEX here be M1 and here M2. So M1, they want to say that it is greater than AL. Why is that? It cannot be exactly AL because AL is in the array. And it cannot be smaller than AL because otherwise we could remove this number from the array and not change the MEX. So M1 is greater than AL and actually M2 is also greater than AL. After that, they say that AL actually greater than A of R2. Let me think. Ah, okay. So AL is greater than R2. So M1 is greater than R2. And this means that there is a number A of R2, something equal to it, which is in AL to R first. So this number is actually presented in this array. This means that we can remove this. We can remove it because the same number is somewhere here. So if we remove it, we don't change the MEX. This means that actually the second inequality didn't hold, this one. This is equality. So this is a contradiction. So you can actually do this operation in linear time, the operation of XOR convolution with a constant. But I didn't do it naively. I actually used bit sets for this operation, and I think it sped up. You can see that it sped up two times the solution. Let me show you. Yeah, so without bit sets it's 236, and with bit sets it's exactly 2 times faster, 218. But actually it was not supposed to... The bit sets weren't supposed to be applied here. Okay, I think that's fine. It's enough for today. Thank you for watching. Did I want to say something? I think no. There are just, of course, there are problems G and H, but they too hard for me. Sorry. Okay, bye.